Welcome back, tech enthusiasts. Today we're diving into the world of specialized processors. Ever wondered what sets NPUs, TPUs, and DPUs apart? Let's break it down. You see, the good old CPU, the central processing unit, has been the workhorse of our computers for decades, and it's incredibly versatile. But as technology marches forward, especially with the explosion of AI and massive data sets, we're hitting a point where general purpose isn't always good enough. We need specialists. Think of it like a sports team. Your CPU is your all-star player, good at pretty much everything. But sometimes you need a dedicated kicker for that game-winning field goal, or a lightning-fast sprinter for a specific relay leg. That's where these specialized processors come in. They're designed from the ground up to excel at very specific tasks that would either bog down your CPU or just wouldn't be as efficient. We're talking about tasks related to artificial intelligence, machine learning, and heavy-duty data management. So in this video, we're going to unpack three of these key players: NPUs, neural processing units; TPUs, tensor processing units; and DPUs, data processing units. We'll look at what each one does, how they're different, and why they're becoming so incredibly important in the tech landscape. It's a fascinating area, and understanding these components gives you a much clearer picture of where computing is headed. Stick around because this is some pretty cool stuff. All right, so first up, let's talk about NPUs, or neural processing units. You've probably heard this term thrown around a lot lately, especially when new smartphones are announced, and for good reason. NPUs are all about accelerating artificial intelligence and machine learning tasks right there on your device. They're essentially dedicated hardware designed to run the complex calculations involved in neural networks much, much faster and more efficiently than a general-purpose CPU or even a GPU could in many specific AI scenarios. Now, why do we even need a separate chip for this? Well, neural networks, the backbone of most modern AI, involve a ton of matrix multiplications and other parallelizable operations. While a CPU can do these, it's like asking a master chef to individually chop every single vegetable for a massive banquet. They can do it, but it's not the most efficient use of their diverse skill set. NPUs, on the other hand, are like having a whole team of specialized sous chefs with an army of food processors, all optimized for that one kind of task. The core idea behind an NPU is to offload these intensive AI computations. Think about features on your phone like real-time language translation, or the camera intelligently recognizing scenes and objects to optimize photos, or even those fun AI-powered filters. Many of these are powered or significantly boosted by an NPU. Without it, these features would either be much slower, drain your battery like crazy, or might not even be possible on a mobile device. So, how do they actually work their magic? Without getting too deep into the weeds of chip architecture, NPUs are built with a focus on parallel processing and specific data types commonly used in AI models. They often have many smaller cores designed to handle these operations simultaneously. This massively parallel structure is key to their performance in AI tasks, allowing them to chew through neural network layers at an impressive rate, making your smart devices feel, well, smarter and more responsive. You'll find NPUs becoming increasingly common, not just in high-end smartphones, but also in a growing range of devices. We're talking smart cameras, drones, and even some laptops are starting to integrate them more prominently. The push for edge AI, that is, processing AI tasks locally on the device rather than sending data to the cloud, is a huge driver for NPU adoption. This means faster response times, better privacy, since your data doesn't have to leave your device, and reduced reliance on a constant internet connection. Consider image recognition, a classic AI task. An NPU can analyze an image, identify objects, faces, or text within milliseconds. This is crucial for features like unlocking your phone with your face, organizing your photo library automatically, or enabling augmented reality experiences that interact seamlessly with the world around you. The NPU is doing the heavy lifting, making these complex processes feel almost instantaneous to the user. Then there's voice processing. When you talk to your voice assistant, the NPU can play a significant role in understanding your commands more quickly and accurately, even in noisy environments. It helps with noise cancellation, keyword spotting like Hey Google or Siri, and natural language understanding. This localized processing means your commands get recognized faster, and the interaction feels more natural and less laggy. And it's not just about these headline features. NPUs also contribute to more subtle improvements. For example, they can help optimize battery life by handling AI-related background tasks more efficiently than the CPU. They might power predictive text that learns your writing style, or manage power consumption intelligently based on your usage patterns. It's these small, almost invisible enhancements that collectively make a big difference in the user experience. The beauty of NPUs is their specialization. They aren't trying to be a jack of all trades like a CPU. Instead, they are masters of one AI computation. This focus allows them to achieve performance and power efficiency for these tasks that are orders of magnitude better than general-purpose processors. It's a testament to how specialized hardware can unlock new capabilities and refine existing ones. As AI models become more complex and the demand for on-device intelligence grows, the role of NPUs will only become more critical. We're seeing them evolve rapidly, with each new generation offering more processing power, greater efficiency, and support for a wider range of AI models. Think about the computational photography in the latest smartphones. A lot of that magic is happening thanks to increasingly powerful NPUs. The integration of NPUs directly into the system-on-a-chip SoC of many devices, especially mobile ones, is a clear indicator of their importance. It means AI capabilities are no longer an afterthought but a core component of the hardware design. This tight integration allows for very low latency communication between the NPU, CPU, and GPU, leading to smoother and more responsive AI-driven applications. This trend towards dedicated AI hardware isn't just a fad, it's a fundamental shift in computing architecture. As we expect more intelligence from our devices, from our cars to our refrigerators, NPUs or similar AI accelerators will be the engines driving that intelligence. They are the silent workhorses making our interactions with technology more intuitive, personalized, and efficient. One of the key advantages of on-device NPUs is the privacy aspect. By processing sensitive data locally, such as biometric information for facial recognition or personal voice recordings, NPUs help keep that data secure and under the user's control. This is a huge selling point in an age where data privacy is a growing concern for many people. Furthermore, the energy efficiency of NPUs is a game changer, especially for battery-powered devices. AI tasks can be very power-hungry. By designing hardware specifically for these tasks, manufacturers can deliver impressive AI performance without completely draining the battery in a few hours. This efficiency is crucial for making AI practical and ubiquitous in mobile and edge computing. Looking ahead, we can expect NPUs to become even more sophisticated. We'll likely see them handle a broader range of AI workloads, support more complex neural network architectures, and offer even greater performance per watt. The innovation in this space is incredibly fast-paced, driven by the relentless demand for smarter, more capable devices. So, in essence, the NPU is your device's dedicated AI brain. It's the component that allows for those smart, responsive, and often magical-seeming AI features that we're increasingly taking for granted. It's a specialized piece of silicon that's reshaping how we interact with technology, making it more personal and intelligent, one calculation at a time. Understanding the NPU helps you appreciate the sheer amount of engineering that goes into making your smart devices truly smart. It's not just about raw CPU speed anymore. It's about having the right tools for the job. And for AI tasks on the edge, the NPU is increasingly becoming that indispensable tool. It's a quiet revolution happening inside our gadgets. All right, now let's shift gears and talk about TPUs, or Tensor Processing Units. If NPUs are often about bringing AI to your personal devices, TPUs are in many ways about powering the massive AI engines in the cloud, particularly those developed and used by Google. These are custom-designed ASICs, application-specific integrated circuits, built from the ground up by Google specifically for accelerating machine learning workloads that use their TensorFlow framework, though their utility extends beyond it. The tensor in TPU refers to the fundamental data structure used in many machine learning applications, especially deep learning. Tensors are essentially multi-dimensional arrays, and neural networks perform a massive number of operations on these tensors. So Google decided, hey, if we're doing this specific kind of math all the time, why not build hardware that's incredibly good at exactly that? And thus, the TPU was born. Google initially developed TPUs to improve the performance and efficiency of their own products. Think about the AI behind Google Search, the magic of Google Translate, the image recognition in Google Photos, or even the AI that helps optimize power usage in their own data centers. These services handle an incredible volume of requests and data, and TPUs were created to handle the AI parts of these workloads at scale, efficiently, and cost-effectively. One of the defining architectural features of TPUs, especially in their earlier generations, is the use of something called systolic arrays. Now that sounds complex, but the basic idea is pretty neat. Imagine data flowing through a grid of processing elements, like waves with computations happening at each step in a highly synchronized and efficient manner. This design is exceptionally good for the matrix multiplications that are so central to neural network computations. It allows TPUs to perform a huge number of these operations in parallel with high throughput and relatively low power. This specialized architecture gives TPUs a significant performance edge for certain types of AI models, particularly large, complex neural networks. When Google first revealed details about their TPUs, they showed some impressive performance and performance per watt figures compared to contemporary CPUs and GPUs for their specific AI workloads. This really highlighted the benefits of co-designing hardware and software, TensorFlow, for AI. While TPUs were initially an internal Google project, they are now accessible to developers and researchers through Google Cloud Platform. This means that anyone can rent time on these powerful AI accelerators to train their own machine learning models or run large-scale AI inferences. This has been a big deal for the AI community, providing access to cutting-edge hardware that might otherwise be out of reach. Google has released several generations of TPUs, each one more powerful and efficient than the last. They've evolved from being primarily focused on inference, running already trained models, to also being incredibly capable at training, the process of teaching the AI model. Modern TPU pods, which are large clusters of interconnected TPUs, can train some of the largest and most complex AI models in the world in record time. The energy efficiency of TPUs is also a critical factor, especially when you're operating at the scale of Google's data centers. Training massive AI models can consume enormous amounts of power. By designing hardware specifically optimized for these tasks, Google can significantly reduce the energy footprint of its AI operations, which is good for both the bottom line and the environment. This efficiency is a key design goal for each new TPU generation. For AI researchers and developers, TPUs offer a powerful platform for pushing the boundaries of what's possible with machine learning. The ability to train larger models faster allows for more experimentation and innovation. Many groundbreaking AI research papers have come out of work done using TPUs, showcasing their capability in areas like natural language processing, computer vision, and reinforcement learning. When you compare TPUs to GPUs for AI tasks, it's not always an apples-to-apples comparison. GPUs are more general-purpose parallel processors and are excellent for a wide range of tasks, including AI. TPUs, however, are even more specialized for the specific types of computations common in neural networks, particularly those built with TensorFlow or JAX. For those specific workloads, TPUs can offer compelling advantages in terms of performance and efficiency. The scale at which Google deploys TPUs is truly mind-boggling. A TPU pod can consist of thousands of individual TPU chips working in concert, offering petaflops of computing power. This kind of massive parallelism is what's needed to tackle the grand challenges in AI, like training models with trillions of parameters. It's this ability to scale that really sets TPUs apart for very large-scale AI. What makes TPUs specialized is their deep optimization for tensor computations and neural network architectures. They often use lower precision arithmetic, like BFloat16, where appropriate, which can speed up calculations and reduce memory requirements without significantly impacting the accuracy of many deep learning models. These are design choices that make sense for AI but might not be ideal for general-purpose computing. The future of TPUs looks bright, with Google continuing to invest heavily in their development. As AI models continue to grow in size and complexity, the demand for powerful and efficient hardware accelerators like TPUs will only increase. we can expect future generations to offer even greater performance, better energy efficiency, and perhaps new architectural innovations to tackle emerging AI challenges. So TPUs are Google's answer to the voracious computational demands of modern AI, especially at scale. They represent a deep commitment to specialized hardware for machine learning, and their impact is felt not only within Google's products, but also across the broader AI research and development landscape through their availability on Google Cloud. They are truly titans of AI computation. Understanding TPUs gives you insight into how a major tech company approaches the challenge of AI at an unprecedented scale. It's about optimizing every part of the stack, from the software frameworks down to the silicon itself, to achieve the best possible performance and efficiency for these incredibly demanding workloads. It's a focused, relentless pursuit of AI acceleration. These processes are a key enabler for the AI revolution we're currently experiencing. Without hardware like TPUs, many of the recent advancements in large language models, generative AI, and other sophisticated AI systems would simply not be computationally feasible or economically viable at the scale they operate today. They are, in many ways, the engines driving the cutting edge of AI. The journey of the TPU from an internal project to a cloud-accessible powerhouse also tells a story about the democratization of AI capabilities. While the largest models still require immense resources, the availability of TPUs allows smaller teams and individual researchers to work with state-of-the-art tools, fostering a more vibrant and innovative AI ecosystem. This access is crucial for continued progress in the field. Finally, let's turn our attention to DPUs, or data processing units. Now, this one might be a bit less familiar to the average consumer than NPUs or even TPUs, but in the world of data centers, cloud computing, and high-performance networking, DPUs are becoming incredibly important. They are, in essence, a new class of programmable processor designed to handle the massive amounts of data flowing through modern servers and networks. So what kind of data processing are we talking about here? It's not about running your everyday applications or training AI models directly. Instead, DPUs focus on infrastructure workloads. Think about networking tasks like routing and switching packets, storage tasks like managing data access and compression, and security tasks like encryption and firewalling. These are all critical functions in a data center, but they can consume a lot of CPU cycles. The core problem DPUs aim to solve is CPU offload. In a traditional server, the main CPUs have to handle not only the primary application workloads like running a database or a web server, but also all these underlying infrastructure tasks. As network speeds increase and storage demands grow, these infrastructure tasks can steal a significant portion of the CPU's power, leaving less for the actual applications you care about. This is often called the CPU tax or infrastructure tax. DPUs step in to take over these data-centric tasks. By offloading networking functions, for instance, a DPU can manage network traffic, implement virtual networks, and handle complex packet processing routines far more efficiently than a general-purpose CPU. This frees up the CPU cores to focus purely on running applications, leading to better overall server performance and efficiency. It's like having a dedicated traffic cop for your data, keeping things flowing smoothly without bothering the main engine. Similarly, for storage workloads, DPUs can manage storage virtualization, handle data reduction techniques like compression and deduplication, and accelerate storage protocols like NVM over fabrics. This allows for faster, more efficient access to storage resources and can significantly improve the performance of storage-intensive applications. The DPU essentially becomes an intelligent endpoint for storage. Security is another major area where DPUs shine. They can offload tasks like encryption and decryption, run firewalls, handle intrusion detection and prevention, and isolate workloads from each other. By performing these security functions on a separate, dedicated processor, DPUs can provide a more robust and secure infrastructure, reducing the attack surface on the main CPUs and improving overall system security. You might hear the term SmartNIC, Smart Network Interface Card, used in similar contexts. DPUs can be seen as an evolution of SmartNICs. While SmartNICs added some programmability and offload capabilities to network cards, DPUs are much more powerful and versatile. They typically include robust, multi-core CPUs of their own, dedicated hardware accelerators for specific tasks, and high-speed network interfaces, making them a fully fledged processing system on a card. Architecturally, a DPU is quite sophisticated. It's often described as a system on a chip itself, containing its own set of programmable CPU cores, usually ARM-based, specialized engines for network storage and security acceleration, high bandwidth memory, and of course, very fast network interfaces. This combination allows them to independently manage and process data paths at very high speeds. The benefits of deploying DPUs in a data center are manifold. First, as we've discussed, you get improved application performance because the main server CPUs are freed from infrastructure overhead. This means applications run faster and can handle more users or larger workloads. It's a direct boost to the primary function of the server. Second, DPUs lead to increased server efficiency and density. If each server can do more useful work because its CPUs are less burdened, you might need fewer servers to achieve the same overall capacity. This translates to savings in power, cooling, and physical space in the data center, all significant operational expenses. It's about doing more with less. Third, DPUs can significantly enhance security and isolation. By handling security functions at the edge of the server, right where data enters and leaves, DPUs can create a strong perimeter defense. They can also help enforce isolation between different virtual machines or containers running on the same server, preventing lateral movement of threats. This granular control is vital in multi-tenant cloud environments. Key use cases for DPUs are rapidly emerging across the tech landscape. Cloud computing providers are major adopters, using DPUs to power their virtualized network and storage services and to offer bare metal-like performance to their customers. DPUs allow them to efficiently manage their vast infrastructure while providing flexible and secure services. In high-performance computing (HPC), DPUs can help reduce communication latencies between nodes in a cluster and offload networking tasks that would otherwise consume valuable CPU cycles needed for scientific simulations or complex calculations. This helps researchers get results faster and tackle even bigger problems. Another interesting application is in building bare metal as a service offerings. DPUs can manage the infrastructure layer, providing networking, storage, and security services, while giving customers direct access to the server's main CPUs and memory without the overhead of a traditional hypervisor. This combines the flexibility of cloud with the performance of dedicated hardware. Several major players are active in the DPU market, including NVIDIA with their Bluefield DPUs, Intel with their IPUs, infrastructure processing units, AMD with their Pensando acquisition, and Marvell. This competition is driving rapid innovation in DPU capabilities, with each vendor bringing unique strengths and architectural approaches to the table. The DPU is sometimes referred to as the third socket in the server, alongside the CPU and GPU. This highlights its growing importance as a fundamental building block of modern data center architecture. It's no longer just about compute and graphics or AI acceleration. Efficient data processing and movement are now recognized as equally critical. Looking ahead, the role of DPUs is set to expand even further. As data volumes continue to explode and network speeds push towards terabits per second, the need for intelligent, programmable infrastructure offload will only become more acute. DPUs will be essential for building the next generation of agile, efficient, and secure data centers and cloud platforms. So while NPUs and TPUs are often in the spotlight for their AI prowess, DPUs are the unsung heroes working behind the scenes to make our data-driven world run smoothly. They are tackling the complex and often invisible challenges of managing data at scale, ensuring that our applications get the performance they need and our infrastructure remains secure and efficient. They are a critical piece of the puzzle in the modern computing stack. There you have it, folks. A quick look at NPUs, TPUs, and DPUs. Each has its unique strengths and applications, and they're all playing a crucial role in shaping the future of technology. From the AI in your pocket, powered by NPUs, to the massive AI models trained in the cloud with TPUs, and the very infrastructure of the internet and data centers being optimized by DPUs, these specialized processors are making things faster, smarter, and more efficient. It's clear that the era of one-size-fits-all processing is evolving. The common thread here is specialization. As computational demands become more diverse and more intense, we're seeing hardware tailored to meet those specific needs. This isn't about replacing the CPU, it's about augmenting it, building a team of processors that can collectively handle the incredible complexity of modern computing. The interplay between these different units is where a lot of the magic happens, enabling experiences and capabilities that were science fiction just a few years ago. So, what are your thoughts? Which one of these specialized processors, the NPU, TPU, or DPU, do you think will have the biggest impact or see the most explosive growth in the coming years? Is there another type of specialized processor you're keeping an eye on? Let us know in the comments below. We'd love to hear your take. And of course, if you found this breakdown helpful, don't forget to like, subscribe, and hit that bell icon for more tech insights. Peace out.